Welcome back to Science Click. Today, Hawking radiation. Our universe is modelled by two theories. General relativity, which describes the fabric of the universe as a smooth surface that can bend, space-time. And quantum field theory, which describes particles as small packets of energy inside quantum fields. These two theories work extremely well and model almost everything we know in their respective fields. But unfortunately, they are currently irreconcilable. Calculations fail to describe the microscopic origin of gravity, the way in which particles, discrete packets of energy, can bend a continuous surface like space-time. Still, it remains possible to study the behaviour of quantum particles inside a curved space-time, if we suppose it to be fixed, neglecting the fact that the particles should influence its curvature. It's with an ingenious calculation of this type that in 1974 Stephen Hawking came across an astonishing phenomenon. Hawking discovers that black holes produce a subtle radiation, which eventually causes them to evaporate. A phenomenon mixing gravity and quantum physics, Hawking radiation. A black hole is a spherical region, a space-time bubble bounded by a horizon within which gravity is so intense that nothing can escape. When surrounded by matter, black holes radiate and can be detected from Earth. However, this radiation is indirect. It comes from the matter outside the black hole. The black hole itself is not really an object, but rather a region. It should not radiate. Near the horizon, space is empty. However, we should not forget about quantum physics. According to quantum physics, our universe contains fields which fill all space and are present everywhere, even in what we call the vacuum. Quantum fields are agitated by fluctuations. They contain waves called virtual particles, some with positive energy and others with negative energy. The vacuum in quantum field theory is simply the state in which these positive and negative waves compensate each other. The fluctuations are still present, but nothing propagates in the field. A real particle is a wave which is not cancelled out and thus propagates. Back to relativity. The natural movement of bodies in space-time is freefall. The fabric of the universe is curved, and objects tend to move straight ahead, causing them to fall. We can represent the curvature around a black hole by a grid which contracts over time. An object at rest remains either stationary or at constant speed relative to this grid. Conversely, an object wanting to oppose the natural movement of the grid is forced to exert an acceleration against freefall. Locally, space-time seems flat. The curvature is only visible on a large scale, as on Earth. Therefore, an observer in freefall does not see anything special, and in particular, she does not feel anything weird when crossing the horizon of a black hole. We have seen that the space around the black hole is empty, and this is true in particular near the horizon. Quantum field theory describes a vacuum as a balance of positive and negative waves. These waves are defined on the space-time grid. They are in a natural state. And a free-falling observer does not detect any particles. She does indeed see a vacuum. But now, imagine an observer who remains parked just above the horizon. To avoid falling, this observer is forced to constantly accelerate. But because he accelerates relative to the grid, he perceives the waves differently. By accelerating with respect to these waves, he receives them with distorted frequencies. In particular, the waves under the horizon never reach the observer who accelerates away. The person in freefall does not detect the horizon of the black hole. For her, the horizon is a place like any other, and the positive and negative waves cancel each other. The space is empty. But the person who prevents himself from falling does detect the horizon, because he accelerates such that some waves never reach him. For him, the positive and negative waves do not cancel. From this point of view, space is not empty, it is filled with particles. It is crucial to understand that the notions of vacuum and particles are relative. Because they move differently in space-time, the two observers see the fluctuations in quantum fields differently. Whilst one sees a vacuum, the other sees particles. Near the horizon, we cannot say whether there are particles or not in absolute terms. This notion is relative. The existence of these particles depends on the observer. Until now, our reasoning was only local. The notion of particles is relative as soon as we have an observer who accelerates, whether we are next to a black hole or in an empty space-time. But in our case, space-time is curved on a large scale. And while the notion of particles is purely relative near the horizon, the further we move away from the black hole, the more staying still, which is an accelerated movement near the horizon, becomes the natural movement. These particles, which exist in a relative way near the horizon, gradually become real particles as they move away from the black hole. Thus, black holes radiate. This is Hawking radiation. The virtual particles near the horizon become real particles far away. The curvature of space-time makes the transition between a region where we need to accelerate to remain motionless and a region where being motionless is natural. We understand that this radiation does not escape from inside the black hole. Nothing comes out. The particles we detect far away originate in the quantum fluctuations just outside the horizon. An intuitive way of interpreting this phenomenon is to imagine the vacuum as a soup of virtual particles which appear in pairs, one of positive energy, the other of negative energy, and immediately annihilate. Usually, these virtual particles cannot become real particles. They remain undetectable, especially because a real particle must necessarily have positive energy. These pairs of virtual particles, one which has a negative energy, must therefore disappear. But inside a black hole, the curvature is so intense that the notions of time and space are reversed. From an external point of view, this allows the particles inside the black hole to have a negative energy. When a virtual pair appears on the horizon, the negative particle thus has a chance to exist. If it is captured by the black hole, it is now allowed to become a real particle, while the positive particle can escape away. By absorbing these negative particles, the black hole loses more and more energy. And little by little, Hawking radiation makes black holes evaporate. Hawking radiation is what we call a thermal radiation. Its spectrum matches perfectly the spectrum that an object would emit due to its temperature. We can thus assign a temperature to black holes corresponding to the energy of their radiation. Large black holes are very cold, because at their horizon the curvature is very mild. They evaporate very slowly. And the smaller a black hole, the more energetic its radiation, corresponding to a high temperature. This is a very peculiar property of black holes. Usually, when a body radiates energy, its temperature decreases. But a black hole that radiates shrinks, and its temperature rises. By losing energy, black holes heat up, and the evaporation accelerates more and more. Having said that, all known black holes weigh several billions of tons, since they form in the collapse of massive stars. Their radiation is extremely weak. Its temperature reaches at most a few billionth of a degree above absolute zero, and it consists only of massless particles such as photons. The evaporation is thus completely negligible. It would take several thousands of billion times the age of the universe to watch them evaporate. Furthermore, the universe is filled with radiation from the Big Bang, the cosmic microwave background. Absorbing this radiation, black holes in reality grow bigger. If the energy of this microwave background decreases as the universe expands, the evaporation might take over, but we would have to wait several 100 billion years. However, there could potentially exist small primordial black holes formed just after the Big Bang, whose evaporation could be ongoing right now. We hope that their radiation could one day be detected. For the moment, Hawking radiation remains a theoretical result. It is currently impossible to detect and based on an approximation, neglecting the effect of particles on the geometry of spacetime. We will certainly have to wait for a real theory of quantum gravity to understand this phenomenon with precision. In particular, the last instance of the evaporation, when the radiation is most intense. Still, it is a very solid prediction. Many different calculations lead to these same conclusions. In 1974, Hawking calculated the gravitational collapse of a star and how the formation of the black hole affects the quantum fields. A more abstract method is to study time not as a real number, but as an imaginary number. This is a technique from statistical physics. The imaginary time loops back on itself, and we recover the black hole's temperature from the length of these loops. Experimentally, we are already studying the phenomenon using analogies. In particular, we can create a flow of fluid in the lab that mimics the conditions of a black hole, with a sort of horizon that separates a supersonic flow from a slower flow. On one side, sound waves can escape, and on the other side, since the fluid is faster, they are captured. These analogies are not perfect, but the equations that describe them are close to those of the true phenomenon, and several experiments have led to promising results. Hawking's calculations and the research that followed helped bridge the gap between gravitation and quantum physics, opening the first paths towards a unification of the two realms. For the first time, a formula, that of the temperature of a black hole, involved all the constants of modern physics, bringing together relativity, gravitation, quantum physics, and thermodynamics. The evaporation of black holes raises many questions and leads to paradoxes in our current understanding of physics. Usually, in physics, knowing its final state, it's possible in theory to deduce the initial state of a system. But two perfectly identical black holes might have formed from two different stars. And after they evaporate, there would be no traces left of what happened. This is the information paradox. The information of what was captured by a black hole seems to be lost forever once it evaporates. Perhaps this information remains at the horizon and is captured and taken away as Hawking radiation escapes, Or maybe the black hole doesn't totally disappear and leaves a tiny remnant that holds all the information. At the moment, we still don't know. Finally, in recent years, Hawking radiation has helped highlight an even stronger paradox, linked to the fact that the virtual particles which separate at the horizon should remain entangled forever. This paradox brings out the limits of our current models, of which some principles might have to be abandoned in the hope of one day finding a theory of everything. One approach to solving this problem is to abandon the equivalence principle, which says that nothing special happens at the horizon. Some believe that there might be a mechanism that somehow violently breaks the entanglement between the escaping particle and the infalling one, a sort of firewall.